oftentimes in real life applications, we don't have right triangles in this situation, nor can we put in auxiliary lines to form right triangles with whatever information that we're given. If we have triangles that don't have a right angle in them, there are still trig identities and trig formulas that we can use that will help us solve those application problems. Now, first, when they say to solve a triangle, what they mean is they want you to find all of the measures of the lengths of the sides of the triangle and all of the measures of the angles of the triangle. So that's what I wrote up here to start with, is just to solve a triangle means to find the lengths of all the sides of the mesh and the measures of all of the angles. Now, an oblique triangle is a triangle that does not contain a right angle. So if you ever see something that mentions oblique triangle trig, they're talking about triangles where you've got the connections between the sides and the angles with your trig relationships, where you don't have a right angle in your triangle. An oblique triangle trig is what we're going to focus on in this video. So first of all, with the law of sines. Now, the law of sines, a relationship between the angles and the sides. When in your triangle, you know angle, side, angle, 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 side, or side, side, angle. Now, with the law of sines, the relationship is that the length of the side of A is to the sine of the angle opposite it, angle A, and that's in proportion to the length of side B divided by the sine of angle B, which is also in proportion to the length of side C over the sine of angle C. And while this is done as 3 in a row, you really just take the proportion that you need with two ratios equal to each other for what information you have and what information you want to have. Now, in the convention of the way that the law of sines is set up, and then in a moment talking about the law of cosines, they're talking about having set up your triangle in your application where the angles are named capital letters, and then once you have the angles named with their capital letters, the sides opposite the angle with the capital letter will have the small case letter name. So if this is angle A, then the side opposite is this one, and that would be side A. And for here, angle C, the side opposite is side C. And for angle B, the side opposite is side B. So the side opposite the angle will have the same letter of the alphabet as the angle, but the angles will be capital letters and the sides will be small case letters. So when you're doing this, if you're following that convention of denoted your sides and your angles, you want to be very careful to be case sensitive. And also, when you're reading the information from the problems themselves, remember the capital letters go with the angles and the small case letters go with the sides. That will actually help you determine which case you have and then which law you should use. Now, with the law of cosines, that law is if you have pieces of information of side, angle, side, or side, side, side. And then the law of cosines is c squared is equal to a squared plus b squared minus 2ab cosine c. And then these other two are just rotations around the triangle depending on which angles and sides you know. If you cover up the subtraction part, this starts by looking like the Pythagorean Theorem. C squared is equal to a squared plus b squared. But remember, the Pythagorean Theorem is only good on right triangles. And we're developing the trig relationships between the sides and the angles of a triangle that's oblique, that doesn't have a right angle. So this start of looking like the Pythagorean Theorem needs to be adjusted because they're not right triangles. And the adjustment is subtract 2 times the sides that were squared on that same side of the equal sign, so 2 times AB, and then the cosine of the angle opposite the side that's on the other side of the equal sign. And then we're working around the triangle, if a squared's over here is equal to the two sides that haven't been listed yet are b and c, so then it's b squared plus c squared, minus 2bc, those same two letters, and then times the cosine of the angle opposite the side from the other side of the equal sign, cosine A. If b squared's on the left side of the equal sign by itself, then that's equal to the square of the sides that haven't been listed yet, so a squared plus c squared, minus 2 times AC times the cosine of the angle that's opposite the side from the other side of the equal sign, so the cosine of B. So you want to really try to see if you can start to see patterning in the relationship between the sides and the angles so that you can have an easier time knowing what these laws are and then also what you're looking for when you apply them. Now let's go look at what they mean by angle, side, angle, 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 side, 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 angle, side, and side, side, side. If you remember from geometry, when you were looking at comparing two triangles and trying to see if you had enough information, abbreviated information, to say that the two triangles were congruent, those pieces of information abbreviated that would guarantee congruent triangles was my angle, side, angle, 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 side, side, angle, side, and side, side, side. So those were the ones that we had that would guarantee congruence with our triangles. So that means that that abbreviated information fixed the triangle. So that gave me enough information to say that I have a specific triangle and not other movements that could happen that would generate different triangles even with that given information. So when I have angle, side, angle, 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 side, side, angle, side, or side, 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 then I definitely have enough information to fix the triangle if I have a triangle. And then if I do have a triangle, then I can use the law of sines for angle, side, angle, and angle, angle, side. And I can use the law of cosines for side, angle, side, and side, side, side. Now, if I do have a triangle part comes into play with this side, side, side. If you have 3 sides of a triangle and you look at the numbers that they have, first of all, they would be given to you in terms of 3 small case letters then equal to the numbers that would represent the sides of the triangle. If the addition of the smaller 2 numbers is not a number bigger than the largest side, then trying to make a triangle out of it, they would just fall and they wouldn't make a triangle at all. But if you have the smaller 2 sides added together give you a total that's bigger than the longest side, then as you bring them together, they will kind of hit kind of like a teepee, and again, it's not going to always be an isosceles triangle. This one just happens to be that, but you'll actually get a triangle. So always when you have side, 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 add the smaller 2 sides together. Make sure you get a total that's bigger than the third side, the longest side, so that you know you're working with a situation that you have a triangle before putting a lot of time into it. All right, so those then will give you a specific set of information. Now, this side angle, I've asterisked because while I will use the law of sines in that case, it's actually something called the ambiguous case. And the ambiguous case is a case where maybe I have a triangle, maybe I don't have a triangle, maybe I have 1 triangle, maybe I have 2 triangles. And I have to evaluate the given pieces of information when I have side angle to make sure that I report all the possible situations it could be, or report that there's not a triangle if there isn't. I will be doing a separate video on the ambiguous case and how you decide, and I'll be putting that link in the description of this video so that you'll be able to go and look at that. Now, when we're seeing with our given information and what desire to find in our problem which cases that we have, what you want to do is draw out a triangle for the problem that you're working, and then put in the values that you know. So, for example, if I know angle A, and I'll put a check mark now that if in a problem they give me the value of angle A, and they give you the value of angle C, and they also give me the value of side B. So as I'm coming around the triangle from stuff I don't know towards the stuff I do know, if I pass by an angle that I have a number on, and then I pass by a side right by it that I have a number value for, and then the angle that I have a number value for, that would be considered, you say it as you pass by and you see that you have the value, that would be considered angle, side, angle. And even if I went up around this way, it would be angle, side, angle. So angle, side, angle happens when you have two angles and then the side that listed is not one of those letters. So that will happen with your angle, side, angle. Instead of memorizing that, though, again, you can just put it on a picture and visualize what's happening. Now, if, when I'm going through and marking my information, I have an angle value A, an angle value C, and a side value A, then as I'm coming around from stuff I don't have to towards the stuff I do have, I have angle, I don't have that side, so I can't say side. So I have angle, angle, side. So that would be your angle, angle, side piece of information. Notice here I have two capital letters for the two angles, and the side that I have matches one of the letters for the angles. So that would be my angle, angle, side. And certainly if you said side, angle, angle, side, angle, angle is the same thing as angle, angle, side. In fact, in a triangle, if you know two of the angles, you have the process to get the third angle, because the three angles of a triangle add up to 180 degrees. So 180 degrees minus the two angles you have will give you that third angle. So if you liked the angle, side, angle part, and you already had that angle, angle, side, you could add together or take 180 and subtract these two angles and get the third angle and then work at the process that way. Now, with that ambiguous case that we need to be really careful about and evaluate what situation we have, so much careful that, again, I'm putting it in another video. With the ambiguous case, that would be side, side, angle. So I would have a side, and then I would have an angle. So as I go around, side, side, angle, or you could say angle, side, side, but I don't want to write that down in the video. So the one that if we did it the other way, it would be something that I'd rather just not write in the video. That's the one that's the ambiguous case. All right, so with this, notice it's one capital, because I have one angle, and two small case, two sides, and one of the small case letters matches the capital letter that I have. So when you have two small case letters and a capital letter, that means you have two sides and an angle. If when you have two sides and an angle, the angle letter matches one of the side letters, that's when you have the ambiguous case. And again, we're going by the convention that it was lettered in this manner. Okay, now, what does it look like for the law of cosines diagram? Well, the law of cosines is side, angle, side. So think side, angle, side. Then as I go around, I say side, I say angle, I say side. And here it's two small case and a capital because I have two sides and an angle. But the two sides I have do not match the same letter of the angle that I have. And that's when you know that, hey, this is a fixed triangle that I actually get. I don't need to worry about the ambiguous case in that setting, and I'll use the law of cosines to get it. And then lastly is if we have side, side, side. So for side, 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 they would all be small case letters, and you wouldn't have any capital letters in that at all, and your job would be to find your angles in the triangle because you already have the three sides. And again, remember that the addition of the smaller two sides has to total up to a number that's bigger than the longest side. One other thing that I wanted to mention as well is that when you're looking at using your law of sines to find your angle, always go to get the smaller of the angles first when there's a couple different angles to find, and the smaller of the angles is the one that's opposite the shorter of the sides. The reason that is because we won't always get, well, our inverse sine function will always give us answers that are between the first the negative pi over 2 to pi over 2 in radians, or negative 90 degrees to 90 degrees. So I won't get that obtuse angle if there is one in a triangle. From the law of sines, I need to get that when I say, well, I have two angles, I need to find the third one from knowing that all three add up to 180. So always get your smaller angle first when you're using your law of sines. And that's true even for your law of cosines. And the other thing is too, that when I have the three sides and I'm looking at finding the angle, I actually need to rearrange the law of cosines to solve it for the cosine of the unknown angle. And you can do that either algebraically so that you get the ratio that the cosine of the angle is equal to, or you can put in the numbers and then rearrange the information in the law, solve for the angle from there. All right, so I'm going to take a few moments to erase this, rearrange the board, and do a few examples. All right, let's look at these two examples. So the first one is where it gives me capital B is 19 degrees, capital C is 81 degrees, and then small case c is 37 centimeters. So I have two angles, and then I have a side. If I think about just the idea of how these are denoted, so angle B, angle C, angle A, and then across from the angles are the sides with the small case letters that match. So B is 19 degrees, C is 81 degrees, and side C is 37 centimeters. So as I go through, I have side angle angle, or I could call it angle angle side. So remember, I say the things that I know as I go around the triangle. So angle, angle, side. And you come from the stuff you don't know towards the things that have measurements that are on them. So angle, angle, side, when I look at my options, angle, angle, side is with the law of sines. Now I have two of the angles, and I know that the total of the triangle is 180 degrees. So if I take 180 degrees and subtract off the total that I have in degree measurements for the two angles that I already know, that's going to give me a degree measurement here of 100 total. So 180 degrees subtract 100 degrees is 80 degrees for my angle A. So that's one of the pieces of information that I need. Now next up for the sides. I already know side C and I already know angle C. So I'm going to use that as one of my pairs in my ratio. And I already know angle B, so I can find side B. So we're going to do side B is to the sine of 19 degrees. So side B is the sine of 19 degrees as side C, 37, is to the sine of angle C. And then I just use my properties of solving equations from here. So to solve for B, I'll multiply both sides by the sine of 19 degrees, and I get B is equal to 37 times the sine of 19 degrees, and then that's divided by the sine of 81 degrees. Now here's where you take a moment and you make sure in your mode that you're in degree mode. And then also the convention is that if my angles are to the nearest degree, I should report my side to 2 significant digits. If my angles were to the nearest tenth of a degree, then I should report my side with 3 significant figures. So when you go and calculate this out and you appropriately round it to 2 significant figures, you'll get that B is approximately 12 centimeters. And centimeters because it has the same unit measurement as the side that we have. Now that will give me B, so now I've got B, and I also know angle A from what we did before. The only piece of information we don't know yet is A. So we're going to go back to the full information that we're given. We should never use rounded values, if possible, in the calculation of new values. We should be using given values, or if we have to use something that we've already found, use it in further out decimal places than what you're going to need to round to, so you don't propagate the error. So A is to the sine of angle A, as C, 37, is to the sine of angle C. Knowing that A is 80 degrees, we're going to have A is to the sine of 80 degrees, as 37 is to the sine of 81 degrees. Multiply both sides by the sine of 80 degrees. I get A is equal to 37 times the sine of 80 degrees divided by the sine of 81 degrees. And that gives me that A is approximately 37 centimeters. So my 80 degrees and my 81 degrees are very close to each other in measure. And so my side C and my side A are going to be very close to each other in measure, in length. And within the reporting of the 2 significant figures, they look to be the same value as an approximation. Okay, so then that gives us all of our information for the solution of that triangle. Let's go to our second example. Here I have the angle A is 19.4 degrees. Angle B is 105.2 degrees. So these are to the nearest tenth of a degree for my angles, meaning I have to report my side in 3 significant figures. And if you don't remember about significant digits, significant figures, I've also put a link for a significant figures video that I posted in the description of this video. So let's come back to the diagram that we already drew for part 1, and we'll put in the information for problem 2. So here A is 19.4 degrees. B is 105.2 degrees. So my picture of my triangle is off, but I just want to try to find which trig relationship I need to use. And then side C, down here, side C, that is 53.4 meters. So now as I come from information I don't know, around through information I do know, this is, I know the angle, I know the side, I know the angle. So this is angle, side, angle case. So angle, side, angle case. So I'm going to take this off so it doesn't get confused with the one that is for problem 1. And we know it's angle, side, angle case, and angle, side, angle is with law of sines. Okay, now notice here that I have 2 of the angles, and I can take my 180 degrees and subtract off the sum of these 2 angles, and the sum of these 2 angles, 24.6 degrees. So I get that my angle C is going to be 55.4 degrees. So for angle C, I have 55.4 degrees. And with this, I have now angle C, and I have side C. So I'm going to use that ratio for sure. And then I'm going to use whichever other one that I need in order to get the remaining. With the first one we're going to do is just say we're going to find side A. So A is to the sine of A as C is to the sine of C. So A is to the sine of 19.4 degrees as side C we don't know, or side C is 53.4 is to the sine of my angle C, 55.4 degrees. Multiplying both sides by the sine of 19.4 degrees, A is equal to 53.4 times the sine of 19.4 degrees divided by the sine of 55.4 degrees. So A is approximately, again, my angle is to the nearest tenth, so I need 3 significant figures, and you'll get that it's approximately equal to 21.5 meters. And then lastly, we want to find our side B. So B is to the sine of B as C is to the sine of angle C. So I have B is to the sine of 105.2 degrees as 53.4 is to the sine of 55.4 degrees. So B is equal to 53.4 times the sine of 105.2 degrees divided by the sine of 55.4 degrees. And when you multiply that out, divide, and then round to 3 significant figures, you get that B is approximately 62.6 meters. So there's my side B, here's my side A, and there's my angle C. Now we're going to do a couple more examples. For our third example, we're going to look at the information small case b is equal to 32 meters, small case c is equal to 21 meters, and capital A is equal to 123 degrees. So when I again look at this, just with the convention of naming our angles and our sides, B is 32 meters, C is 21 meters, and angle A is 123 degrees. So as I come from the information I don't know towards the cluster of information I do know, I have a side that has a measurement, I turn the corner and there's a measurement on that angle, and I have a side that has a measurement. So this is side, angle, side. And for side, angle, side, we're going to use the law of cosines. Now, this is one of the ways that we can do the law of cosines, but what we have here is we know B and C, and we know angle A. We want to find side A. So that is A squared is equal to B squared plus C squared minus 2BC cosine of A. So I have A squared is equal to 32 squared plus 21 squared minus 2 times 32 times 21 times the cosine of 123 degrees. So now when you go through and you work this out, you get that A is about 46.87211, but my angle was to the nearest degree. There's no point something, it's the nearest degree. So my side are to 2 significant figures. So 2 significant figures, I want to round to the ones place here to get my 2 significant figures. So my A is approximately 47, and my measurement is meters. Now that we have A, I have an angle and a side opposite, and so I have a case that I can use my law of sines. To get one of the other angles. So when I do this, I want to find one of the other angles. Let's say that we want to find angle C next. And again, I want to look at which one would be the smaller angle. This one already has an obtuse angle, so my other two angles are going to be acute anyway. It's not as much of a big deal with this, but just to be in good habits, if I have two angles that are unknown, I should always go after the smaller angle first. And the smaller angle will always be across from the smaller side. 21 is a smaller number than 32. So we'll go C is to the sine of C as A is to the sine of A, because I now have side A and angle A. So I know side C is 21, is to the sine of, I don't know, angle C, is equal to, now A, I don't want to use a 47, that's rounded. I want to use as further out than where I want to round to by several decimal places. A is to the sine of angle A, which is 123 degrees. Now when I look at a proportion, I multiply the extremes times the mean is equal to the product of the means. So I have 21 times the sine of 123 degrees is equal to 46.87211 times the sine of angle C. Divide both sides by 46.87211. I get 21 times the sine of 123 degrees divided by 46.87211 is equal to the sine of angle C. And now I'll just do the inverse sine of both sides to get the value for C. So angle C is the inverse sine of that expression. And when I do that and I round that to the nearest degree, I get that angle C is 22 degrees. And then now that I know angle C is 22 degrees and angle A is 123 degrees, I can get that angle B is equal to my 180 degrees minus the sum of these two angles, so minus 145 degrees. So angle B is approximately, and for each of these I should put approximately, angle B is approximately 35 degrees. So there's my angle B, my angle C, and my side A to solve that triangle. Okay, next up, and the last example for this video is to have the information side A is 111 inches, side B is 131 inches, side C is 158 inches, and I want to just find angle A, not solve the whole triangle. Well, these are three sides. And remember, the smaller two sides added together have to be a number bigger than the longest side for it to make a triangle. But when I add 111 plus 131, I'm at 242 inches, which is bigger than 158. So we have a triangle. Now, side, side, side is what we have because they're all small case. So that's the case that goes under the law of cosines. And I want to find angle A. So to find angle A, the angle that's in the cosine expression in law of cosines matches the letter of the side that was squared on the left-hand side by itself. So that's A squared is equal to B squared plus C squared minus 2BC cosine A. And I can actually solve this in the variables first and then plug in the numbers. So I want to solve for cosine A, but I have to get the term that has the cosine A on a side by itself before I can do the division to take the coefficients off. And since this is a minus, I'm actually going to add 2bc cosine A to both sides and subtract the a squared off so that I don't have to worry about messing up with the minus signs. So this is 2bc cosine A. I added that over here, and I'm going to subtract the a squared is equal to b squared plus c squared minus a squared. Now, you're trying to get at angle A, and the cosine is acting on angle A. So now you want to divide both sides by 2bc. So cosine A is equal to b squared plus c squared minus a squared over the 2bc to get the cosine on a side by, of A on a side by itself. And then I want to find A. So A is equal to the inverse cosine of b squared plus c squared minus a squared over 2bc. So my A is equal to inverse cosine for this question, 131 squared plus 158 squared minus 111 squared divided by 2 times 131 times 158. And when you key that through, and then also look, all these sides are with 3 significant figures, so you should report your angle to the nearest 10th of a degree. So when you work this out and you report your answer, A is approximately equal to 43.9 degrees. So that gives you several examples of how to solve oblique triangles. Also just maybe to find a particular piece of an oblique triangle. And again, I'll be doing the ambiguous case, the side-side angle, in another video.